So Ian is a product consultant at 475 High-Performance Building Supply, and they are based in Bend, Oregon. As a product consultant, he supports his clients with water, air, and vapor control strategy, foam-free design details, and heat recovery ventilation design. Ian is a certified passive house tradesperson, a certified HERS rater, and a BPI building analyst. He combines his experience in canvassing, energy auditing, on-site data gathering, data analysis, energy modeling, and whole home diagnostic testing to support his clients with their high performance projects. Ian has been with 475 since 2018 and serves California, Oregon, Washington, Idaho, Nevada, and Arizona. Don't hesitate to reach out to Ian. He would love to connect with you. And we'll do the Q&A at the very end, probably the last 15 minutes or so. So please put your questions in the chat. And welcome, Ian.
Perfect. Thank you, Dee. Thank you for the introduction. And I will just go ahead and get started since we've got a short window here and there's a lot to cover. So again, thank you everyone on the call for jumping on today and allowing me the opportunity to present this training. And do feel free to reach out to me after this call. We'd be more than happy to chat with you. So brief note on 475, we were started by two architects in Brooklyn, New York. That's where most of the folks live and work, is over there on the East Coast, but I am based in Oregon on the West Coast. And it was started by two architects who wanted to bring in materials from Europe to be able to meet the passive house standard. So that's how 475 was born about 12 years ago in an effort to build high performance buildings here in the US. So this presentation today, this is the foam-free, airtight, and resilient making high performance building enclosures presentation. And I will just jump through this stuff here and get right into it. So here we go. Here's our presentation. So what is high performance, right? Your clients have an idea of what high performance means. You probably have ideas of what high performance means. We've got 6 general points of what a high performance building could mean, right? We want high levels of comfort when we're inside the home. We want healthy levels of indoor air quality. We don't want to have wildfire smoke getting in there. We want the home to be energy efficient and reduce our bills. We want the home to be resilient in the face of extreme cold, extreme hot. It sounds like California's had a bit of that, both of those over the last year. We also want the home to be very durable, and we want it to be low embodied energy. So the passive house standard, or passive house certification, is a great way to meet all of those goals, right? You can make the home very energy efficient, resilient, comfortable, high levels of indoor air quality. And the passive house principles can show us the way to that. And the passive house principles are based on no thermal bridging, no heat heat and energy recovery ventilation, high levels of air tightness, triple pane, high performance windows or glazing, and really high levels of insulation. And while I don't think that every single project needs to be built to the passive house standard or needs to be certified, I think it can be really valuable for you all as designers to work with a certified passive house consultant to help you with your design needs, because there are certain tweaks that they can make and certain efforts that they can make to show you where you might be putting too much insulation and where you could move that and put it elsewhere while also saving costs in the process. So does passive house deliver comfort and energy savings? Absolutely. It reduces heating and cooling loads by about 95%, and it can reduce whole home energy usage by 75%. So it's a very, very useful tool with respect to energy efficiency. It also helps support our renewables transition. There's lots of solar in California, lots of batteries going in, lots of Teslas, things like that. So if our building is using 75% less total energy, that's 75% less solar panels we need to pay for and find space for to put on our buildings to become net zero. And so, as we move forward on our little planet here, our industry does strive to push further, right? Our industry's gotten very good at honing in on energy efficiency and the amount of energy that buildings consume year over year. And now the new focus really is this embodied energy, or the amount of energy it takes to actually produce the materials and produce the building itself. So like I mentioned, operational energy is the energy that the building is using year over year. It's the amount of kilowatt hours that you use. It's the amount of therms that you might use if you're connected to natural gas. And that's relatively the same year over year. There might be some fluctuations with nasty weather, but essentially that's year over year, and we've gotten good at reducing that. Embodied energy, on the other hand, is the amount of energy that it took to produce the raw materials that actually create the building, right? The insulation, the wood framing, the concrete, the finishes, all of that stuff. And that's what we really have an opportunity to focus on moving forward. So this is a chart by Architecture 2030. It shows a variety of insulation products and their associated embodied energy for a wall that's 234 square meters large and at an insulation value of R20. So this is the same wall, same insulation value, but very large differences in the amount of CO2 either emitted by the products or sequestered. And you can see some of the foam insulations are the worst offenders, whereas the natural plant-based materials have sequestered the most carbon, before they get to market. And so there's a really great tool called the Building Emissions Accounting for Materials Calculator, the BEAM tool. And this tool can be used to help you guys as designers select products in the project to help address this embodied energy. And 72% of the emissions actually come from the concrete, the insulation, and the cladding in the building. So if you really just hone in on those three, you can do a lot of good right off the bat. And so why does embodied carbon matter, right? Well, you can see here on this chart, we have the gray lines. This is your operational carbon. It's the year over year carbon being consumed by the building. So it's, small amounts year over year, right? Because we're insulating our buildings well, we're using LED lighting. But the amount of energy that it took to produce that building itself, that's the blue lines there, that's quite a lot right at the front end. So if we want to reduce our emissions as soon as possible, it's important to address the embodied carbon of our buildings. And I like to say, why not? There are new products every single day that come on the market that seek to address these issues, right? These are straw bale panels produced on the East Coast on the left. We've got hemp bat insulation being produced in the US, hemp being grown in the US in Idaho and shipping out from there, cost comparative to something like mineral wool. And then we also have a variety of wood fiber distributors here in the US, and they do a blown in material, a bat, and a wood fiber board. So this is an opportunity for you folks as designers to hone in on this embodied carbon and make an effort to address it. And so this is the foam-free presentation, right? So I'm going to tell you a little bit about foam itself and how it relates to high-performance buildings. So foam insulation is very popular. It's got a really great R value per inch. It comes in rigid boards that can be put on the outside of the walls. It also comes in the spray foam application that you can see in the image here. And so really high R value, and it comes at a relatively affordable cost, right? Spray foam may be a little bit more expensive, but it's used. That's why it's come to dominate the market. But there are a few issues with it. It's made from petrochemicals. This guy's suited up from head to toe and connected to a respirator because there is unhealthy off-gassing, and there have been cases where there have been long-term off-gassing over time. So there are health concerns. And then mainly we want to talk about performance, right? This is the high-performance building enclosures presentation. So foam can be installed like any other product improperly, right? We can see this image at the bottom left here, which is a thermal imaging image, and you can see that there are air gaps and insulation gaps in that installation. So nothing's perfect. We do have to rely on folks to do these installations. But mainly spray foam especially doesn't address thermal bridging through the studs. Thermal bridging is basically a pathway for heat to move in and out of the building very easily. So you can see in this wall here, we've got 2x4 studs, assuming there's no rigid insulation on the outside, that there's a direct pathway for heat. Wood has an R value of about 1 per inch. Those look like 2x4 studs. So you've got R3.5 every 16 inches within the wall, and then you've got a really high R value in the cavity. So spray foam does not address thermal bridging. It's not putting insulation on the outside to really make the wall perform its best. And then with respect to air tightness and things like that, foam is an inorganic material. Wood studs are organic. They shrink and expand based on temperature differences, humidity differences, and the foam can actually crack away from the wood framing members. Foam is also, it will shrink over time as well. It's not dimensionally stable. That's the word I was looking for there. So can we make better assemblies? We absolutely can. And there's hundreds of folks, thousands of folks doing it every single year in the USA. So today I'm going to talk about the robust enclosure. There's a lot of components of high performance. There's a few on the list here. This is certainly not the entire list of the components of a high performance building, and these are all going to be different. Some of them the same based on the client and the person designing the home. So, So once the fire codes, structural codes are taken care of, what are we thinking about with the robust enclosure? Well, we want to shed water off the building, right? If we have bulk water enter the building, we're going to have issues very, very quickly. We also want to have really great air control toward passive house levels of performance, and we'll get more into why that's important later. We want to have resilient vapor control to avoid mold in our walls. And we also want to have really great thermal control towards that thermal bridge 3 construction, eliminating those heat pathways in and out of the building. So water control, pretty straightforward, right? We don't want to tuck our rain pants into our rain boots, and we want to have overlapping layers that shed water away from the building. And even more importantly now, we're using materials in the market that are less durable when it comes to moisture. So OSB and plywood is a really great example. Plywood is made from one slice of the tree all the way around. So each sheet is a continuous layer of wood. So what that means is the wood can still use capillary action to move moisture. So if you have a bulk water incident, leak in your roof, let's say, and water's getting in your wall and you have plywood, that plywood will actually soak up quite a bit of that water and help spread it out to dry it out. So plywood can take on more water and it can dry out more quickly, whereas OSB is, small layers of wood that are glued together, and that ability to move the moisture away is interrupted. So OSB can't take on as much moisture, it can't spread it out to assist with drying, and it takes a really long time to dry. So it's just a material that makes our buildings less durable. And as we know, if water is left unchecked, it will destroy our building. So that's first section on the robust enclosure, which was water control. And now we're going to focus on air control. And air control fundamentally affects energy efficiency, thermal bypass, indoor air quality, and a few other things. So when we're talking about air tightness, we're talking about, all 6 sides of the building if our building is a nice little square, right? We're talking about the ceiling, the walls, and the floor. And we're also talking about the transitions between raised floors and windows and things like that. And regardless of if your building's big or small, air tightness is very important. And what's really great is it's very easy to control air tightness and measure air tightness with a blower door test. Blower doors are installed on typically the front door of a home. All the windows are closed and you suck air out of the house. You depressurize the house to a level of -50 pascals with reference to the outdoor air pressure, which would be 0. And you get a value for the amount of cubic feet of air that actually move through the fan. So you can actually test the air tightness of the home very easily. And by using a calculation involving the cubic feet per minute moving through the fan and the cubic volume of the home, you can determine how air leaky the home is. And that is the ACH 50 value. ACH 50, like I said, is just a calculation of the amount of CFM of air going out of the house and the cubic volume of the space. So higher the number, more air leaky, lower the number, less air leaky. The passive house certification is 0.6 ACH 50. Old historic homes are 5 or greater. I've done blower door tests on manufactured homes that are above 15 ACH 50, so just exceptionally leaky. And what's important with air control is it really impacts energy efficiency. This is the first passive house project that was built in Germany. And this is the passive house software here that's looking at the annual heating demand and the heating load of the building at a variety of ACH 50 values, right? So this chart on the right-hand side, we've got a few different ACH 50 values, and that's being plugged into the energy model. And that energy model is kicking out the associated heating demand and heating load. So as you can see here, 0.6 ACH 50, your heating loads are about 12 watts per square meter. If your building was blown at a 3 ACH 50, your heating system has to be twice as twice as large. So, air tightness fundamentally affects energy efficiency and the size of the systems you need to purchase to keep your home at a comfortable temperature. And don't take my word for it. NREL just did a study here, and from what they studied, infiltration is the largest contributing component to heating loads in all climate regions studied. The slide I showed you before, is probably climate zone 4, coastal California. You're not needing as much heating as those climate zones, but it still makes a difference with respect to air tightness. And so air also fundamentally affects the R value of our insulation. If you guys have ever been outside on a cold, windy day with a fleece on, you will know that wind cutting through the fleece, it's not keeping you warm, right? As soon as you throw a hard shell over that and you're preventing that air movement through the fleece, that fleece is keeping you nice and warm. Or if you're wearing the fleece inside, then there's no wind. So thermal bypass can really degrade our R value. So the best practice to ensure that our R values are going to be what they're spec'd at is to put air tightness on both sides of the insulation and to prevent convection loops through the insulation. So not only energy efficiency, indoor air quality and thermal bypass, air control fundamentally affects the amount of moisture that can get into our walls. This little chart and these images here on the left-hand side, this is from the Building Science Corporation, a study that was done over the course of one winter, and they wanted to understand how much moisture gets into walls through one piece of gypsum board. So that image on top, this is at an interior temperature of 70 degrees and a 40% relative humidity. And so over the course of one winter, there was about a third of a quart of moisture or water that got through that piece of gypsum board. Now, if you go to the image below and we put a 1 inch by 1 inch square hole in that same piece of gypsum board, we can actually get up to 30 quarts of water. So 100 times as much water is getting into the wall via air than through water vapor. And that's why it's also very important to control air, to control moisture in your building. So when it comes to designing the airtight layer, we want to use robust materials, right? We want to use materials that will hold up over the long term because the building should last 100 years, hopefully. We want to simplify the details. There's a builder on site that's doing the work, so we don't want to make it too complicated. We want to consider the sequence because sometimes that airtight layer is also your water control layer. So we don't want to make something airtight, but then make something not watertight, right? If it's shingled improperly. We want to seal up all the penetrations. And then if there are any damages to this airtight layer, we want to make sure it's repairable and can be verified. And we also want to make sure it's protected. And so now I'll touch a little bit on why we want to prioritize the inboard air control layer because it has additional benefits for our building. So interior air control, right? This means inboard of your insulation layer. This is already where you want your vapor control layer. We're humans, we're breathing, we're showering, we're cooking, we're producing lots and lots of moisture inside the home. This is why all of your house wraps on the market are vapor open because we're producing lots of moisture. And as that water vapor seeks to go outside the building, we want to make sure things are vapor open and we're not trapping moisture in our wall. So an inboard vapor control layer is going to prevent water vapor from getting into your wall in the first place. And it can also double as an airtight layer because as we know, we can have 100 times more water get into our wall via air than via water vapor. And so if we have a cold climate, that sheathing layer on the outside can get really cold. And if we have conditioned air that's warmer sneak into that wall cavity and hit that cold surface, you can have condensation. It's the same reason why a cold, tasty drink in the summer is wet on the outside, right? You have warm, humid air that engages with that cold surface, and that cold surface becomes a condensing surface. And so, like we talked about, we want to protect the airtight layer. So a service cavity is a great way to do that. Inboard of this airtight smart vapor control layer. This is where you can run your services, electrical outlets, things like that. It's also protected from the occupants when they're hanging art or punching holes in the wall. So protection of this airtight layer is very important for long-term durability. And then for the air barrier itself, right, we want to use really robust air barrier materials. Drywall is oftentimes used as an air control layer, and that's great because it is on the interior side of the insulation, so it's in the right place, but it's very susceptible to damage, very susceptible to the occupants who are in the building, and it can be degraded very easily. And so just to touch back on foam one more time with respect to air tightness, right? Spray foam applications are touted to be airtight, and initially they typically are. However, installations can go wrong. Installations can be put on to materials that are too wet, cold, or dirty, and there can be delamination of the foam from the framing members. Foam is not dimensionally stable, and it can shrink over time, which can create small air gaps. So it's not a reliable airtight layer. And so the robust connections around windows and things that connect to our airtight layer in the wall are very important. Traditionally, sealants have been used, but they embrittle and fail over time. There are new approaches with tapes and solid acrylic adhesives that are also protected from the occupants that are a much better approach. And so with this interior air control layer, we do have to consider sequencing, right? So this is a great example of a builder who put up a strip of an airtight vapor control layer before they installed an interior wall. So now it's very easy to tie in that airtight layer on the interior across the rest of the wall. Whereas if they had forgotten to put in this strip here, you'd have to tape to both sides of the framing member, using more tape, taking more time, and all of that. Oops. So raised floors, these are areas where we want to have the airtight layer be continuous. So there are simple ways for creating those floor transitions, from the interior side of the wall, around the frame floor, and back to the interior side of the wall on the second floor. Very simple step to do. Window penetration sealing, again, this is a place where foam insulations are used quite often, Baccarat and caulk, but there are better options on the market, tapes that have been designed to be airtight for the long term using solid acrylic adhesives to really create a strong bond. And then there are also pipe and wire penetrations and sealing gaskets that are available. And it's very easy to seal those up without creating a huge mess of spray foam cans and spray foam kind of sticking off of the wall. All right, so now we're moving on to the section of vapor control with respect to the robust enclosure. We've covered water, bulk water, air, and now we want to talk about water vapor as well. So in our older, poorly insulated buildings, there's not much insulation, right? There's not much R value, which is resistance to heat. So a lot of heat can flow through that wall very easily, right? In the summertime, the sun comes out, it's baking the side of the building. It can drive a lot of heat inward very easily. In the wintertime, since there are low levels of insulation in the walls, you need a very strong or powerful heating system to actually make the house feel comfortable. So a lot of that heat is moving through the walls very quickly. So when it comes to moisture issues and moisture problems, older buildings do really well, right? Because there's so much heat moving through the wall, they're able to dry out very easily. When we push forward and we go towards, passive house levels of performance or really high R value walls, this specific example is, the image on the right-hand side. This is an example, I think in New England, And this is a passive house project, right? So it's very cold outside and then it's warm inside. So you can see the exterior walls are very cold, whereas in the image on the left-hand side, the walls are actually a bit warmer because there's a lack of insulation there. So again, image on the left, it can dry out very easily. Image on the right, this is wintertime. The exterior walls are cold. And the heating systems inside that building are actually much smaller, right? Because you don't need a gigantic heating system to heat your building. So the opportunity for these highly insulated walls to dry out is less. So now we really have to focus on water vapor to make sure we're controlling that element of moisture to make sure that we don't have problems, because the walls just don't dry out as fast. They're not as resilient, so to say, with respect to water. So in general, water vapor moves from areas of high concentrations to low, and also from warm areas to cold areas. So in the wintertime, when you have warm air inside the house and you have cold air outside the house, water vapor is going to be trying to migrate out of the building. So from a best practice perspective, to keep water vapor out of the wall, we want to have a vapor retarding material on the interior side of the wall cavity, and then we want to have a vapor open wall outboard of that. That way, if any moisture does get into the wall, it can dry out, since that's the natural vapor drive. If we flash forward to the summer and we have, really hot temperatures outside, cool air-conditioned temperatures on the inside, that water vapor is going to try to drive into the building. And so this is where we don't want to trap water vapor in our walls, right? So we want that vapor retarding interior layer to be vapor variable and be able to open up and allow for inward drying. So this is why we question installing vapor dams or foam-based insulation products, right? This is a home that's got, really great thermal control on the outside. It looks like maybe 2 inches of rigid insulation. This is going to, keep the house nice and warm in the wintertime, nice and cool in the summer. However, its ability to dry out can only be done in one direction and in one season during the summer, right? The only way this wall is going to dry out is if the sun comes out in the summer and tries to push some of that water vapor inwards. So basically, the most robust way to build a wall is to be vapor open both directions. That way you can ensure that there aren't any moisture problems. And so foam, it's hydrophobic and it doesn't aid in drying. We talked about that plywood material that can kind of soak up water and help spread it out and help dry out that bulk moisture that might be sitting in the wall. Foam doesn't do that, right? Essentially, the water doesn't engage with it. The water doesn't move through the material at all. It just stops it in its tracks wherever it ends up being. And so foam can create wetness, right? We talked about the natural vapor flows in the winter and in the summer. And this is another Building Science Corporation study here. On the y-axis, we have relative humidity. And on the x-axis, we have time. And basically, where they put the humidity sensor in this test was on the interior side of the sheathing layer, because that is the condensing surface in the wall. So they wanted to see in 4 different walls here what the moisture, what the relative humidity, or how the relative humidity would change at that interior face of the sheathing layer. So there were 4 walls constructed. One that was 2x4, one that was 2x6. Those are the red and orange lines there. And then another wall that had advanced framing with 1 inch or 4 inches of XPS insulation on the outside. Those are the blue lines. And so, that XPS insulation, it's vapor closed, doesn't allow water vapor to move through it. And you can see here, and I will note also that this was a study in Minneapolis, Minnesota. So, a bit colder than Central California, but a good study nonetheless. Basically from about October through, April or May, you have relative humidity levels that are above 80% at that interior face of the sheathing over the course of the winter. So is this going to cause the building to fall down? It's anybody's guess, but mold does start growing at above 80% relative humidity. So in the wintertime here, we have that water vapor that's trying to migrate out of the building, but it's unable to do so because we have a vapor closed insulation product on the outside. Whereas the other two walls, you can see that that water vapor is able to move through the building. So all in all, foam just makes our enclosures less tolerant to moisture. It's kind of like using OSB over plywood. If you use OSB and it gets wet, you're just going to set yourself up for potential issues. Similarly, foam, if we do have moisture problems, it can be more disastrous. And so, to hone in on this even a little bit more, there are many sources of moisture, right? We've talked about vapor diffusion. On the bottom there, that 28 ounces convection, that's air movement. We know that air can move, 100 times more moisture into the wall than through vapor diffusion. We can also have flank diffusion. This is where we have, some type of structural member that gets in the way of our vapor control layer. It can also be thought about like a thermal bridge. A thermal bridge is a bridge from the inside to the outside of the building that can move heat in and out of the building. This flank diffusion can be a vapor bridge, essentially, where your vapor control layer is interrupted. And then we can also have wet construction, right? So there's no absolute protection against moisture. I'm not sure why that's crossed out. I'll have to update that. But essentially, the best thing we can do to provide long-term durability for the building is to allow it to dry towards the inward and to be able to dry towards the exterior side as well. So that's why we like to see vapor open sheathing at the exterior side of the building, so we can dry outward and inward. There are also buildings that are constructed where the structural sheathing is on the interior side of the wall. So this is an example here of a project where they used the OSB as the primary airtight layer and vapor control layer on the interior side of the wall. They taped the seams of the OSB to ensure that it was airtight. And then they're hanging all their insulation on the outside of the building. So if there are any moisture issues towards the outside of the wall, it's not going to degrade their structural sheathing element. With respect to water vapor, rain screens are something that 475 likes to promote. They're a best practice approach to managing water vapor in your walls. A rain screen is defined by RAINA, which is a new rain screen association. It's defined as the space between the backside of your cladding and your WRB. And so that rain screen space can be a variety of depths. But basically, the deeper the cavity, the more airflow you can have through that cavity. And that airflow helps dry out your wall more quickly. You can see in some of these images here, there's probably that image in the middle. You have some vertical battens going up that are creating probably a 3/4 inch ventilation channel. Then you have your horizontal battens being installed for your vertical siding. If you were doing horizontal siding, you wouldn't necessarily need those vertical battens in addition. So the thing to remember here is the wider the rain screen is, the better. You guys are in California, so if you make that depth too wide, you do open yourself up to issues with respect to fire and embers. There's a really great organization in Seattle called RDH, Building Science, and they've done some really nice presentations on rain screens recently. I think they're free to download, and you can check them out. With respect to fire, since we are in California here today, they say that basically a rain screen once you're at 2 inches, that's when it starts to become a problem. If you're less than 2 inches deep of a rain screen, which typically you would always be, you're not going to have issues with fire. Essentially, if it's narrower and narrower, there could be a little bit of flame that gets into that rain screen cavity. However, the fire itself will suck all of the oxygen out of the cavity, and the flame won't propagate. So yeah, rain screens, definitely best practice in terms of managing moisture. So there's also new technology with respect to our water resistant barriers, our house wraps. Older technology relies on micro pores. These are products that are stretched. They're typically a single layer product that's stretched to create micro pores. And those little holes in the material are what allows water to escape. And that water migrates through those holes via air. But you can imagine this is our watertight layer, right? We don't want to put micro tears or micro holes in our watertight layer. So it does degrade the water tightness of our materials and the air tightness. There are new products on the market that use a monolithic membrane, 3-layer products that have a fleece on the interior and the exterior side that protect this monolithic layer in the middle that actively transports water vapor along a molecular chain. So these end up being, much more airtight, in this case, 100 times more airtight than typical products on the market. Additionally, around windows, we don't want to create vapor dams similar to like XPS rigid insulation on the outside of a wall. Typically, flashing tapes are all vapor closed, and that's very important on the window sill where you can have, a flat sill that could have standing water on it for a very long time. But on the flanges at the header and the jambs, this might as well be vapor open tape so that we can allow for that outward drying. So when it comes to these interior vapor control layers, there's a variety of products that can be used. We saw that image prior with the OSB and the taped seams. Plywood can be used for this. And then we can also use vapor variable membranes or vapor intelligent membranes. And each of these products have hygroscopic characteristics. So hygroscopic characteristics means that as these materials experience higher levels of humidity, they are able to open up and become more permeable. So you can see OSB adjusts its perm rating, its permeability, about from 0.5 to 2 perms. So it doesn't open up a whole lot, right? It's not able to dry out and move water more quickly. Plywood, on the other hand, opens up to about 10 perms. And then we have the best case scenario, intelligent vapor control membranes opening up to 13 perms. And when it comes to vapor control, there are 3 classes. A class 1 vapor control layer is below 0.1 perms. Class 2 is between 0.1 and 1. Class 3 is between 1 and 10. So if you're above 10, you're not considered a vapor control layer. So like we talked about earlier, naturally the vapor drive in the wintertime is towards the outside of the building. And in the summer, it's going to be towards the inside of the building when we're cooling. So we talked about having a vapor retarding interior air and vapor control layer, but we also want that layer to be able to open up and allow for inward drying. So this next slide here will put things more in perspective, I think, for you guys here. So on this chart, this is for one specific product that's on the market. This is the specific vapor curve that exists for that product. So it's the way that this material changes its permeance based on the amount of humidity it's exposed to. So on the left-hand side here, we have permeance on the y-axis, and then we have relative humidity down there on the x-axis, the horizontal axis. So you can see when we're heating our home in the wintertime, our interior humidity is probably going to be 30 to 50% relative humidity. And at those levels of humidity, this interior vapor control layer is going to be very vapor closed, below 1 perm, which is great because we want to keep the water vapor out of the walls and out of the ceilings of our projects or out of our homes. But when we flash forward to the summer, there may have been some moisture that got into that roofing assembly some way, somehow, and now you have the sun coming out, baking the wall or the roof, and that might be driving water vapor towards the inside of the building. So once this specific material encounters, 85, 90% relative humidity, it opens up to 13 perms, which allows for that inward drying, and it's not considered a vapor control material. So an example of this, this is a WUFI hygrothermal analysis of a specific roofing project in Davos, Switzerland. This is an unvented roofing assembly. So this is not a vented attic type of roof. This is a completely unvented roof assembly. So you have no ability to dry outward, right? You have no ability to allow that water vapor to dry out and escape, similar to a vented roof. So this is a worst case scenario, 40-degree pitch roof, very cold, climate at high altitudes and a north-facing roof pitch. So this is looking at one specific roof assembly and using different interior vapor control products on the inside. So as you can see, OSB or the polyethylene sheet, these don't open up, right? Their perm ratings don't change so much when that increase in moisture happens, that increase in humidity. So they're not going to help that ceiling dry out. When you're looking at vapor variable or vapor intelligent membranes, you can see that over the course of 10 years, in this specific example, the roof was able to dry out and allow more moisture to escape over time because of those that ability to open up when higher humidities are being exposed to it. So my last section here is thermal control, and we'll get through this quickly so we have time for questions because I know we have a hard cutoff at 1 o'clock today. Thermal control is very important. We want to prevent thermal bridging through wall studs. We want to prevent thermal bridging through these balconies on the Aqua Tower in Chicago. This is a very cool building, but essentially in the wintertime, it looks like a radiator that's heating up the earth, right? It's just driving that heat out. And the reason it's doing that is because those concrete balconies have no thermal break as they transition to the interior floors of the building. So any heat that's being produced on the interior side of the building is going down into that concrete floor, and it's being carried out to the outside without any thermal break. It's just a thermal bridge to the outside. So this is a nice image of some isotherm charts. The isotherms are on the bottom there, and then on the top we have different wall conditions. So on the right-hand side, you can see that those two structural elements are completely broken with that yellow insulation layer. And you can see the isotherms at the bottom look like a nice, neat rainbow. There's no bubbles or anything like that, which is exactly what we want to see. So there's not much heat moving in and out of the building at that point because that thermal bridge is thermally broken with a thermal break. The image in the middle is kind of the retrofit application. So the image in the middle, you can tell that the isotherms chart looks a little bit better. And what we're doing there is we're actually just increasing the path that heat has to take to enter and exit the building. And even doing that is helpful with respect to reducing the amount of heat that either moves in or moves out of the building. And so with respect to that rigid insulation on the outside or those thermal breaks, if it's being placed on the outside of the building, we really like to see that vapor open insulation so that you can allow for outward drying in the wintertime and avoid some of those moisture issues that could occur. And then there are also a lot of really great thermal break products. Some of them are foam based. These rails that are used on the sides of buildings to hold up rigid insulation on the outside. If that metal was attached right to the building, that's more of a thermal bridge. If we put a piece of foam or fiberglass in between that, we're providing some R value and providing a thermal break to help with the energy and performance of the building. Let's see here. So this is just one example wall assembly, and I will end it right here since we're right close at the end. So going over the robust enclosure, what we just talked about, right? We talked about water, air, vapor, and thermal control. So in this specific example, we've got the back vented rain screen, and we have the WRB, our exterior air control layer, and WRB, and that's preventing bulk water from getting into our building, which is great. Then we want to talk about air control. So air control, we've got the exterior product, which can be our wind-tight product. It's preventing that wind washing through the insulation. It's preventing that thermal bypass. And then we have our interior primary air control layer, which is preventing conditioned air from getting to the wall assembly and creating a problem, right? It's preventing that condensation issue. That interior air control layer is also doubling as a smart vapor control material, so keeping water vapor out of the wall. But if water vapor does need to move, it will allow for that inward drying. And then what's fun about this double stud wall is with the thermal control, that thermal break is actually in between those 2x4 studs, right? And that insulation that's settling in between there is what's creating the thermal break. And with that, I'll just finish it up with a summary. So we want to have those continuous control layers, right? We want to have properly placed high performance materials so we can readily get greater tightness and smart vapor control. We want to minimize or eliminate the use of plastic foams and make our assemblies more durable and sustainable. Always use that blower door so you can check the air tightness of your buildings. And then we want to protect your control layers as well with sacrificial finishes. So thank you so much, everyone, for your time today. Really appreciate it. And I'm happy to take any questions.
Thank you so much, Ian. And if people want to unmute themselves and start a discussion, that might be the easier way to go. I don't see any questions in the chat box right now. I will say that I really appreciated your explanation of vapor barriers. I think that's really the first time it made complete sense to me. So I appreciate that.
That's great. Yeah, no, that's great to hear. I think we're always trying to refine the way we talk about it because it can get confusing. And what's really great, I think, about this presentation is we're sort of isolating water, air, and vapor and talking about those separately, even though that air and vapor control layer can be one layer in your building, or it can be two, right?
Mm-hmm. And correct me if I'm wrong, but I don't think you talked about, doing different scenarios depending on what climate region you're in. Is that correct?
I didn't know. Yeah. So I didn't talk specifically about, climate zone 3, coastal California. But that's definitely something I can talk about, on a follow-up call with folks who have questions. Definitely.
Okay, great. Well, any questions, anybody? Going once, going twice?
There's got to be one person with one question out there.
Well, I'll throw in a question. I just did a ADU and we could not get our cathedral ceiling to pass Title 24 without putting foam in the ceiling. And we were under strict height, requirements. So I think in that kind of scenario, you're probably putting your exterior insulation and then
Yeah, so that, what was that?
In that kind of scenario, you're probably having to put your exterior insulation on top of your roof rafters.
It can depend, right? So in that project, since you had, stringent height restrictions, and maybe you already had the framing depth of the ceiling already ironed out, you might have needed that spray foam to hit the R value that you needed. But if we were designing that on the front end and maybe had a little bit more flexibility with the height restriction or the depth of the ceiling, then you could just use an interior air and vapor control layer with a plant-based insulation like cellulose, and you could forego the rigid insulation on the roof. The rigid insulation on the roof is really great for preventing thermal bridging, and that would be the best practice option there, right, to prevent thermal bridging through that framing. But yeah, foregoing the spray foam and going with an interior air and vapor control layer with a plant-based insulation is possible. And we can take a closer look at those projects, right? Coastal California, you're going to be more forgiving with those in terms of moisture control. If we're up in, northern Canada in a very cold climate and we have a highly insulated roof, you may be forced to put rigid insulation on the roof deck. But in your climate, we could probably get away with just plant-based insulation and an interior air control layer.
Great, thanks for that. I don't know why I didn't think of calling you.
Well, you'll think about it the next time, so that's great.
Exactly. Oh, okay. Let's see if there's something in the chat box. Just from Julie saying thank you, Ian. So, gosh, doesn't seem like there's any questions. Should we just wrap up?
Sure. Yeah, well, thank you so much, everyone, for your time. And thank you, Dee and Tara, for putting this together and providing me the opportunity to chat with everyone. I will send out, or I think Tara's going to email everyone on the call just a little email from me so that you have my contact information if you would like it. And yeah, happy to follow up again. I live in Oregon. I do travel to California with 475, so I could stop by an office here and there if I was already in the area. And don't hesitate to reach out. We like doing consulting and we like helping folks with their high performance projects.
Great. Thank you so much. And thank you everybody for coming.
All right. Take care. Thank you.